And here it is. So we are in this GitHub LLM for genomics training, and we are now in the third tutorial. So here is the link to the Google Colab. There you go. And we'll use my Hugging Face models, which are here. So, by the way, on my Hugging Face, there are a lot of large language models that I've pre-trained. So you can use all of them as you want. And today we'll use this model, Mistral DNA, 17 million parameters, which was trained on the whole human genome. Let's go. So this is the Google Colab, so you can run it, of course, for free. We'll first clone the Mistral DNA GitHub. I don't have any more GPU, so I will use a CPU, but everything is fine, it will work. Let's clone the Git first. Then after we have to install a BioPython module. So let's go. So the aim while it's installing and downloading, so the aim here is to use a pre-trained large language model, a model that have never seen any mutation. So that's why we call it zero-shot learning. So we use a model that was not trained or pre-trained for a given task, but we then find a trick to use it for this task. So that's why it's called zero-shot learning. The concept of zero-shot learning is you have a model, it was not trained or pre-trained for a task, and then you still find a way to use it for this task. So NVIDIA SMI does not work for me because I don't have a GPU, because I used the GPU too much, but in your computer it will work. So let's load the libraries. So that's the idea of zero shot. Zero shot is you never used any training samples, zero training samples. So that's why it's called zero shot learning. But still, you find a way to achieve your task. So we'll see how we do it for with an LLM. So the LLM has only seen DNA sequences. It has seen all of the DNA sequences of the human genome, but it has never seen any mutations. But still, we can predict the impact of mutations. So let's go. Um, let's set up the maximum of the memory. I'm defining a function to read the FASTA file. Here are the different models I can use. I'm going to use this. Let's use the 17 million parameters model. Here we have the tokenizer, the associated tokenizer. So we download it. Here we load the model, the model architecture with the weights. So here it is. We have downloaded the model from Hugging Face. So you see it's a Mixtral for causal LM. This is architecture, which is a Mistral model. It uses an embedding, so 4096 tokens. So it means a word. So this is a number of words in the DNA sequence that I have defined. I could have defined more words, by the way, but that's what I defined. So it corresponds almost to k-mers of size 6. So it's more about, yeah, k-mers size 6, but it can be a bit more also, because we use byte per encoding. We have 8 layers of 8 blocks of the Mistral transformer block. It uses mixture of experts. So here it is, mixture of experts. So to reduce the burden when you compute. So it means that it will, although there is in our model 17 million parameters, as I have 8 experts, but only one expert that will be used each time. because there is a router where each sequence is going to an expert. It is a way to effectively reduce the number of active parameters while computing. So this is a way to reduce the computations. So how many parameters? I said 17 million parameters. Let's start to use it. So I took a sequence here, and I wanted to say, okay, what is the embedding? So what happens if I take the sequence, I give it to the model, and I take the hidden states, the last layer of hidden states. So when I do that, I can do min pooling or max pooling as a way to summarize information along the sequence. And I have, for each sequence, I have a vector value, numerical vector value. This is how the DNA sequence is represented inside the model. Okay, so for each sequence, no, yeah, this is a hidden state. Yeah, if I want to, yeah, if I want to take my to see my if I want to see, yeah, the the mean of the hidden states, the mean along the sequence, this is a vector corresponding to my DNA sequence. Okay. And it has a size of 4096 tokens. Now let's think about it. How can we use an LLM to predict the impact of mutation? So we have an embedding. So it means that you take a DNA sequence, and you can compute an embedding, so a mathematical vector representing your DNA sequence. What you can assume is if a mutation has a strong impact, then the distance between the wild type sequence, so the sequence without the mutation, and the mutated sequence, so the sequence with the mutation. So here we have the wild type sequence for the mucoviscidose, gene. So it's just a part of the gene, by the way. So the gene is CFTR, so it's a gene that if you mutate it, it can be responsible for mucoviscidose. So this is a wild type sequence, and this is a mutated sequence. So you have a deletion, basically. Sorry. So basically, you have a deletion here that is leading to the disease, the Mendelian disease, which is mucoviscidose. Okay? So it's here, the wild type, and here is the mutation, mutated sequence. And if you want to look at this, if you want to look at it, so this is in French, but in English. Oh, sorry. So in English it's called cystic fibrosis. So sorry for that, because me it's written in French. So cystic fibrosis. So this is a disease. I'm sorry, I'm French, so that's why for some disease I make some mistakes. So let's compute for the two sequences their embedding, and then let's compute the distance between the two embeddings. And we'll use the Euclidean distance, so the L2 norm. Okay, so this is what we're gonna do. And let's compute it. And then once I compute it, you can see that the distance is 145. Okay, so there is no real unit behind that, of course. But what we can assume is that the higher the effect of the mutation, the higher the distance between DNA sequences. Because you can imagine that in the space, the latent space of DNA sequences, if so, you have your wild type mutation, your wild type sequence. If you have a mutation that does not have a strong effect, it will change a little bit the position in the space of the DNA sequence. But if the mutation has a strong impact, it should change a lot the position of the DNA sequence in the latent space. So that's how we can use uh, a pre-trained LLM for zero-shot learning of uh, mutational effect. So let's do it with, for instance, a mutation that does not have an impact of the CFTR protein sequence. So what I did is I changed the codon ATT by the codon ATA. So it means that it's still coding for the same amino acid, but the protein sequence is not affected. So here you have the ATT, and I changed by ATA. So you have a mutation from T to A, but you still have, so it's a mutation that does not have an effect on the amino acid sequence. Let's compute it. Let's compute so you can see here that the distance is lower, much lower, 27. So you go from 148 for a mutation that is known to be involved in cystic fibrosis to 27 for a mutation that is known to be silent. So it's a silent mutation that should not have much impact. So it does not have an impact on the protein sequence. It might have a small impact on the mRNA, by the way. So what I thought is, okay, let's take single nucleotide polymorphism, so mutations that are SNPs. So in my data, you'll find I collected some mutations, and I took the reference allele and the alternative allele. So what I thought is, let's use this LLM to compare mutations at exons. It means mutations that are thought to change the amino acid sequence, and compare them with SNPs, I mean, in situation where it changes the codon, and compare them with SNPs at introns. So meaning SNPs that are not expected to change, that will not change the amino acid sequence of the protein. Of course, there are exceptions. It's a bit simplified. There are also splicing variants that are in introns, but let's assume that mutations that are introns that don't modify the amino acid. But in average, what you expect is, in average, if you have a bunch of SNPs that are in exons, okay, and if you have a bunch of SNPs that are in introns, you should observe that SNPs in exons have a higher impact, mutational effect than SNPs in introns. So that's what I did. So what I did is I made a FASTA file of alleles from SNPs in exons. So it's ref here. The alternative alleles of SNPs in exons, so the corresponding alternative alleles, and same for introns. So you have the reference alleles for the SNP in introns, and you have alternative alleles for SNPs in introns. So let's do it. Then I'm going to read the FASTA files. So here are some FASTA sequences. And then I made a sequence to compute the embedding. A function, sorry. I made a function to compute for a list of sequences their embeddings. Here I'm using this comp embed function to compute the embedding for both reference sequences and alternative sequences, so reference alleles and alternative alleles. And then I compare the embedding, okay? So it's just a function at what we did before. And then let's do it. Um, let's compute the L2 distance, so the Euclidean distance between reference allele in exons and alternative allele in exons, and compare them with alternative allele in introns to reference allele in introns. Okay, so here I'm computing. It's taking a little bit of time, but still it's quick. Also, I'm in the CPU, just to say. So here is just the vector of L2 distances that I've computed for the exon SNPs. And then let's compare using a box plot. Using box plots, the two sets of distances. So two sets of mutational effects. And what we find is very interesting is you can clearly see that in average, your exon SNP, they have a much higher mutational effect than intron SNPs. Okay, you can see it here. So you can see that the effect of the exon SNP that you expect them to have a higher effect, of course. You can see that they are higher than neutron SNP. So it was a really nice validation. And let's see if it's significant. So you can use a student t-test between the two sets of distances, the two sets of Michel effect that you have predicted. Or if you want, and if you assume that it's not following a normal law, you can use the Wilcoxon text. Let's do it. And you can see that in both cases, the p-value is much lower than 5%. Okay, so here it's 7, 10 to the minus 7, and here it's 3, 10 to the minus 6. So you can see that the difference is indeed very significant. So this was a tutorial to predict the impact of mutations using LLM. So the idea, as I said previously, is to use a pre-trained LLM that has never seen any mutation, but to use it for a novel task that is predicting the impact of mutation. So that's why we call it zero-shot learning. It has never seen in this training data mutations. So because it has never seen any mutation, we call it zero-shot learning. So the idea with this model is that you can use them to predict the impact of any mutation. So you can have a mutation score, of course. So this kind of approach can be compared, for instance, to conservation scores at basis or other approaches. All right. So I hope this tutorial was clear for you, and I will make another tutorial on generating artificial sequences in yeast. All right. Bye bye.